Hello, welcome back. In this lecture, we're going to go ahead and analyze the maximum moment that a beam can take. Take a look at the picture I'm going to post on a board over here. You see this beam is subjected to a moving load, a uniform load of 300 pound per foot, and also concentrated load of 4,000 pound. And the beam itself weighs about 200 pound per foot. So what we're going to try to here, we're going to figure out how we're going to calculate the maximum moment that based on this moving load can be applied at point D. If you look at the problem, we have done this in class before, you can see this, there's more reaction than equation we have to figure this out. But one of the things we talked about before in influence line, and if we go ahead and just replace where we're going to make the cut at D, replace them with the pin and apply positive moment, then we can draw basically our influence line. It's just like when you have this line, and this is basically the deflection shape of the beam when you make those cut. And you have your beam kind of drop down. If this drop down, this one going to go up straight. And this is be the shape of your deflection. Later on, we're going to come back and we want to know why we use H here. Again, we talked about how we're going to calculate these H value. And let's first do it the old way, calculate this, and then we're going to come back and go use the influence line. Now we're going to come back here and we're going to put the load on a beam and a moving load, and we're going to use where we have the positive moment, and the whole beam is going to be 200 pound per foot, which is going to be linear all the way through. And then in this area, we're going to add the 300 pound per foot moving load plus the concentrated load applied at point D. When we have this, from here on, let's go figure out the reaction so we can figure things out. One of the first things we do, as we talked about it before, we're going to go ahead and draw the free body diagram. When we draw the free body diagram, we try to solve this reaction. How are we going to do that? Let's cut the beam right here. It's easier for us to go ahead and calculate it here because we have two reaction, and it'd be easier if we take a moment about point B, we can calculate the reaction BY. So we're going to go ahead and take a moment. Summation moment about point B is equal 0. Going counterclockwise is positive. In this area, we're going to have AY multiplied by 5, and that's going to be negative, so it's going to be minus AY times 5, plus the load is, we converted the uniform load to a concentrated load of 1,000, and it's going to be about 2.5 feet from this end. So this distance is basically 2.5 feet. It's right at the center, and it's going to be plus 1,000 times 2.5, and that's equal 0. If you do your calculation here, AY is going to come out to 500. That's 500 pound. And if we do summation FOI and BY comes out to the same thing, it's going to be equal. Also, this is the same as the BY. Equal same thing, 500 pound. Now we have that. We have more equation than reaction, so we bring this up to this side of the beam. So what we did, we first analyzed member AB, and then when you come back to BE, and these reaction force is going to be opposite with the same magnitude on this side. And we can go ahead and calculate this. So BY is 500 here, and it's going down. And now we want to find out what EY is. That's what we're looking for. Or we can take a moment about CY, or can we take a moment upon EY and do summation of Y. So let's do the summation moment about E is equal 0. Going counterclockwise is positive. We start from this angle, it'd be 500 times, that'd be 15. I got, no, 15 and 5 will be 20. 20, the whole beam is 5, 5, 10. So now we're going to go ahead and take a moment about point E. It's going to be 500 times 20. And the sign is going to be positive, and then it's going to be plus the 1,000. And that's going to be multiplied by 17 and a half. Then we have CY itself. It's going to be times 15. And minus CY times 15. Then the next one we have is the other load, 4,000 and 7,500. So it'll be 4,000 times 10 plus 7,500. times 7.5. And that equals 0, so EY comes out to, no, CY comes out to 8250. Doing summation FOI equals 0, going up is positive. We're going to find out that EY comes out to, you can do the work yourself and check my number, and EY comes out to 4750. Good. All right. So far we have calculated the reaction. We got everything we need to find the maximum moment at point D. So let's make the cut. We're going to go ahead and cut it right at D. And right here at EY, we figured out to become 4750. Then we had the 7,500 pound right here. Okay, this distance D is 10 feet. So D is 10 feet. Okay, so this is 10 feet. And remember, we have 500 times 10 makes it 5,000. So don't use the 7,500 right here, because this 7,500 is for 15 feet. But we're going to make the cut at point D right here. And from D, it was 10 feet. Therefore, you're going to have 5,000. And then right at the load at D itself, we had 4,000. Let's separate this. So now we make the cut, as we talked about it before. We got to replace the cut with shear, in both directions. I'm not going to show the horizontal one. And this is VD, and then we're going to have the moment. Remember, moment is going to go both way positive. So this moment is going to come up this way. That's going to be MD. All right. And how are we going to do this? We're going to take a summation moment about this point, and we can calculate MD. So we're going to say summation moment about point D is equal to 0. Counterclockwise is positive. That's minus MD right there. And then I'm going to have 4750. That's going to be plus 4750. And that's multiplied by 10. And what else I had? I got this. Now I got to do the 5,000 minus 5,000. And that's time 5. I think I got everything right there. We got this one, we got this one, and that one equals 0. And go ahead, check my calculation. MD should come out to 22.2 kips per foot. This is the way we did it before. Now we're going to go ahead, do the same thing using the influence line. So I got to erase the board, put a pause, just watch this. I'm going to snap my finger, and you're going to see the board be erased. Okay, now we're going to go ahead and we're going to do the same thing here by using the influence line method. And what we're going to do, instead of using the load and we figure out the reaction, we're going to go ahead and apply unit load. And if you remember, we had taken this same beam here. I'm not going to draw the thickness of the beam, just the beam itself right here. We had the reaction here at EY. And then we have a load here, which is a unit load at point D, and that's going to be about 10 feet away. And the next thing we have is the roller right here. Let's continue this a little bit. And we got the roller right here, and that's 5 feet from here, 5 feet. Then beyond that, we're going to cut the beam right here. Let's cut the beam right here so we can analyze it. It's going to be BX going this way and going the other way. And now we're going to go ahead and continue the beam on this side, which is this is the AB. AB right here, and we're going to have reaction here and reaction this way. Okay? So there's no load here. That's good. Therefore, this is 0, and this becomes 0. Now, I know this is 0. Only thing I have is a 1, and I got cy right here. And then I got ey, and this is easy to calculate, really. I don't have to write this down. You should be able to know how we do that. Take a moment, just like here, just like we did before. Take a moment about point ey and calculate cy, or take a moment about cy, calculate ey, and that's going to come out to this going to come out to 0.333, and then up here become 0.667. All right. Now we have that calculated. We're going to go ahead and we're going to make the cut at D. So if we're making a cut at D right now, we know this is a 0.33, and the unit load is over here, so not going to help us out. Then I'm going to have the shear here and a moment going this way. And the moment is going to be this time that distance, 10. So MD, again, you should know that. How we're going to calculate that is summation moment about point D with this multiplied by that distance. So MD comes out to 3.33. 3.333 is good. It goes on for a long time. Now, what does that mean? That means this is H is equal 3.3.3. This H and H prime should be equal. Just because I didn't do a good job drawing it, what happened, the distance, these two distances are equal. And we talked about those in class before. We said H is equal L1 over the L and L2 over the L. And this kind of come out to the same. So our H in here comes out to 3.3. Now we're going to go ahead, apply the load based on this diagram here and calculate the maximum moment. And so figure out what MD comes out to. We're going to use this influence line right here, and we're going to put this whole positive load right here and calculate it. You have the uniform load here. So the uniform load is going to be based on multiplied by the area underneath this triangle. So they're going to be, go ahead, 500 pound per foot, and you're going to multiply by 1/2. H is 3.3, and that's going to be multiplied by the distance, which is 10. Then that was just due to the uniform load. Then you have the concentrated load. The constant, be careful here. The concentrated load only multiplied by the height of the triangle and not by the area. So it's going to be plus 4,000 multiplied by 3.3. Then you're going to have to go to this side and deduct this. So it's going to be minus. What we have here, it's only 200 pound per foot. So we got minus 200 pound per foot multiplied by the area of the triangle, which is 1/2, 3.33, and that is time 10 also, equal 0. So if we calculate this, MD going to come out to 22.2 kip per foot, just like last time. Same thing. Okay, so we did this both different way. We came out the same way, and that's how it's done. Thank you.